Find V out if the gain is infinite or if the gain isn't infinite. First, I'm going to take the equation that holds true for all op-amp configurations. Then, notice that the gain here is infinitely large. V plus is 0. See that it gets grounded. V out, since this is a negative feedback configuration, is expected to be finite. That means that V plus is going to be very close to 0. If I name this node X, the voltage here, Vx, is going to be very close to 0. This concept is known as a virtual ground. Now I'm ready to take a KCL on this node, node X, and the currents that flow inside are the same as the current that flows outside. So, how much is the current that flows from V1 all the way to here? Should be V1 minus 0 over R1. Remember, Vx is close to 0. Plus, the same for V2. Plus, is there any current flowing from this parasitic resistor from the ground all the way to here, or the opposite way? Well, the voltage here is the same as the voltage here, and the same as the voltage here, which is 0. The ground has 0 voltage too, so 0 voltage, no current passes through this resistor. So the current that would flow from here to here, due to this parasitic resistance, is 0. This will be equal to the current that flows from here all the way to here. So it should be 0 minus V out over RF. Now this is very easy. In this result, basically we have something like a classic op-amp summing configuration, where we sum two voltage inputs and scale them by some factor over here. So we saw that this parasitic resistor plays no role in this configuration when the gain is infinite. So it's like it doesn't exist. Alright, let's check the next case. Again, I'm going to write the equation that I know is true for all op-amps. The gain is finite. The output is finite since this is a negative feedback configuration. How about V plus? V plus is 0 since this is grounded. Well, that means that V minus now is not 0. It's not very close to 0. It must have a value because the output has to be finite. So we have to multiply something finite here with something finite to get this result. That means that this is also finite. And more importantly, not 0. Well, how much is this? Well, we do something very easy. We take this here, multiply this here, minus V out over A. That's how much is V minus now. And if we name this again with something that we are comfortable with, let's say X, the voltage now at Vx is going to be how much? Minus V out over A. Notice that now we don't have a virtual ground. Why? Because the gain is not infinite. Now, again, let's take the KCL for this node over here. So, it's V1 minus Vx plus V2 minus Vx over R1 or R2. And now, notice that this voltage, and this voltage, and this voltage, which is the same, is different than the voltage here. So that means that there must be a current flowing through this resistor, in this case. So I'm going to add another current here. A current flowing like this, a current flowing like this, and there must be also a current flowing like this, all summing up to this current. So for the parasitic resistance, it should be 0, the voltage at the ground, minus Vx over Rg. All of this must be equal to Vx minus V out over Rf. This minus V out over A is how much? It's Vx, correct? Now I'm ready to replace Vx over here. And now this is very easy. From this point onwards, we just solve by putting all Vouts in one side, V1 and V2 on the other side, and then solving for Vout. Which would finally mean that Vout is nothing but. And now we found Vout. Notice that when the gain here, A, is infinite, well, this whole thing becomes 0. So it's 1 over Rf. All of this is to the power of -1. Therefore, this is minus Rf times this. Like previously when we have an infinite gain here. So our result is correct. This is basically an op-amp summer, a summing amplifier. I covered the summing amplifier in detail in a video over here in the op-amp playlist. Check it out. Anyway, study well, take care, bye bye.